A black hole is a singularity with such high density that nothing, including light, can escape its gravity. A black hole forms when a large star more than 3 solar masses collapses in on itself, forming a singularity. A singularity is a point of zero volume and infinite density. Black holes survive by absorbing gases and masses that they collide with in space. A star less than 3 solar masses will become a white dwarf or a neutron star when it dies. Theoretically, supermassive black holes can also originate from the collection of gases in space and collapse at the center of quasars and galaxies. The black hole at the center of the Milky Way is called Sagittarius A and has a mass millions of times that of our Sun. Here you can see the structure of a black hole. What you see surrounding the singularity is called the event horizon. Everything you see outside the event horizon, the excretion disk, contains only matter that can escape the gravity of the singularity. The radius of the event horizon is called the Schwarzschild radius, which will always be proportional to the mass of the collapsing star. The radius of the excretion disk is 3 times the Schwarzschild radius. You may wonder about the curvature of the photon ring, the light you see slightly outside the event horizon. Well, Einstein's theory of general relativity states that any massive object warps the spacetime around it. American theoretical physicist John Wheeler gave his interpretation of general relativity, saying that spacetime tells matter how to move, and matter tells spacetime how to curve. What this means for black holes is that spacetime surrounding it is warped so light takes a shorter, curved path to reach it, which explains the light ring's appearance. The light itself is not curving, it is the spacetime around it that is warped. Spacetime curving in on itself around a black hole is also the reason light cannot escape according to general relativity. Since light has no mass and travels at a constant velocity, when it passes a black hole it will not accelerate. However, the frequency of light must be changed by the spacetime distortion in order for the event horizon to appear in the visible light spectrum. This is known as the gravitational redshift or blueshift effect. The color emitted versus the color observed within the visible light spectrum will shift either blue or red. A blue shift means shorter wavelengths, whereas a red shift means longer wavelengths. This is how you can observe the red coloration outside of the event horizon. It is because of this effect, along with the distortion in spacetime, that the photon ring appears as it does. To show how light interacts with black holes, I programmed a 2D visual simulation I'd like to share. You can see how when light enters the event horizon, it is absorbed by the singularity, but everything outside it is able to escape. You can also see the curve in light, which is due to the cosmic distortion or the warp of spacetime. Now for how black holes die. The biggest supporting theory for how black holes die is through Hawking radiation. Hawking radiation is the theoretical black-body radiation that supposedly is released outside a black hole's event horizon due to relativistic quantum effects. In space, particles annihilate each other when they come into contact. Stephen Hawking theorized that when these particles approach a black hole, one will fall into it while the other escapes. The black hole absorbs the negative particle, and the positive particle escapes, making it appear as though it has been emitted. So the black hole is losing energy as it absorbs the negative particles and releases the positive ones, meaning it will eventually run out of energy and die. You may wonder why black holes are even remotely relevant when the nearest one to us is 1,560 light-years away. Well, black holes revolve around the theory of general relativity, which accounts for everything in space that is big. However, general relativity is completely incompatible with the theory of quantum mechanics, which accounts for everything in space that is small. What's so cool about the study of black holes is that at any point we can either bridge the gap between these two fundamental theories, or we can completely disprove one or even both. Thanks!